Good afternoon, this is Schweitzer, and we're looking to start a pretty big section here on how do we mathematically describe the concentrations of a solution. So some sort of ratio is needed, and sometimes I use the analogy of stuff per stuff. Like it's not real complicated in the sense that we're looking to, really, there's a lot of ways you can do it. And with that being said, let's get a pen here. With that being said, there's like a dozen different ways they describe, a beaker with the stuff that's dissolved in it versus the solvent. So you could do the stuff that's dissolved versus the mass of just the solvent, the mass of stuff dissolved to mass of solvent, moles of dissolved for mass of solvent, moles of dissolved for a liter of solvent, moles of dissolved versus the total volume. So there's all these different ways, and they have molarity, molality, normality, percent by mass, percent by volume, mole fraction, density. There's all these ways to do this, but they're all kind of the same thing. They're just a relationship. The one we'll be focusing on is called molarity. Molarity is a mathematical relationship of moles of solutes. That's the stuff that's actually being dissolved. This is moles of the stuff dissolved, and then the liters of the whole solution. Okay. It's symbolized with the capital M, and it's called molarity. A more common, just general thing you got to know here is that the moles, if you're given the formula of the substance or a molar mass, this thing could be jotted back and forth between the grams of solute. Like you could get the mass of stuff dissolved in there if you have the molar mass. Of course, if you have the molar mass, you just need the formula. Like for, let's say, if it's ammonia, then you would just need that formula, and you could add up the molar mass for this thing, and then you would have the grams per mole, and then you could flip from grams to moles and solve what you need. So typically speaking, we have play this little game where we're just solving for a missing variable, and we will see some of that today as we go through. This is show the big grams. You can go back and forth to grams. All right. All right, so let's try some different variations of the molarity problems. How do I solve for various variables? So mathematically, keep in mind that molarity equals moles per liter. I often simplify the mathematics of anything really we do in chemistry as A, B, C, D, is that things just move diagonally. Okay, move things diagonally. As long as you don't have any addition and subtraction, you can move things diagonally. And very important, okay, do not trap. Okay, you're missing your lone variable or what you want to find. Variable on the bottom. If you solve for the bottom, if you leave it on the bottom, then you're going to get the reciprocal of what you're looking for. So this guy actually is over 1. So anytime if I want M, well, M it's already solved for. What if I want the moles? Well, all I'm going to do is move things diagonally. So the liters is going to have to get up here. So in this case, this guy's going to have to go up there. So it's going to be molarity times liters equals moles. And this might seem juvenile for some people, but for some people it really is. Again, that moved up top, moved diagonally. So it's still over 1, but that's this guy. Some people need a refresher of this, guaranteed. Then that next one, what if I want liters? Okay. Well, in that case, I got to get liters off the bottom. I cannot leave in the bottom. So I'm going to take my molarity equals moles per liter. I'm going to move my, let's get a different color here. I'm going to take my liters and move them to the top. I'm going to take my, so for 1, my molarity, I'm going to move it down to the bottom. So my liters will equal moles never got touched, but these two switch spots, and over molarity. Do not trap your liters on the bottom. Now again, we also have this whole thing, molarity over 1 equals moles per liter. And you could plug in what you have and cross multiply and divide to find the other one. I don't like doing that as much. You should be able to do some straightforward algebra and solve what you need. Okay, so with that being said, let's take a moment here and let's solve out for what we need. Okay, so 5 moles of CO2 dissolved in 25 liters of water. What's the molarity? So I always write the formula out. Moles per liter keeps me from making mistakes. That's what I'm doing. And I want this guy. Okay, so I just plug in what I know. 5 moles divided by 25 liters. And that's 1/5, or plug in your calculator. Now I have 2 sig figs here, and I have 3 sig figs here, so I'm going to use the smallest number, which is 2. Alright, so 5 divided by 25 is just 0.2. But I'm going to leave this as 2 sig figs and 0.20 moles per liter. So we're going to start following some of these rules a little closer. Alright. Alright, there we go. Next one. Alright, so in this one here, again, we'll review it again. An aqueous solution has 0.058 molarity. If the volume is 500 milliliters, how many moles of mass are present? Okay, so I'm looking for molarity equals moles per liter. I want to solve for moles, so things move diagonally. Molarity times liters equals moles. And then I'm going to convert the moles over to grams using the molar mass of the NaCl. Now, the NaCl is going to be 58 grams per mole. Okay. Alright, so let's do this here. I got molarity, which is 0.58 times, I got, this has to be in liters, so that's moving it over. That's 4 sig figs, by the way, so 0.5000 liters. Alright, that's 4 sig figs times 0.5. Back that up. Half a liter, basically. Alright. It's got a pretty accurate measured value. And this is going to equal my moles. So 0.58 divided by, or times 0.5. Now what I do, essentially, is when I start, all I do is I say I have 2 sig figs here, and I have 4 sig figs here. I just want to make sure in the end, do all my math, don't worry about the sig figs till the very end, but I want to make sure in the end I have 2 sig figs. So this is going to be 0.29 moles. Okay. And then I'm going to get rid of moles. I'm going to go to grams. 1 mole is 58 grams. And then I could do a little better job adding up if I want to be more precise off the periodic table. But times 58 is 16.82. So 16.82 grams. Okay, so now just round that off to 2 sig figs, which would be right here, and it's just going to be 17 grams. Okay. Again, just look at your numbers you start with. If they both have the same number, that's fine. I always take the smaller one too. That's the majority of our sig figs that we ever do. Alright, moving along. Alright, so looking for a tank of water, has a concentration of this. To dissolve 5 grams of oxygen. How much volume is needed? Okay, so we're looking for a liter. Molarity equals moles per liter. And then solving for this is going to be liters equals moles per molarity. And that was so simple, just moving things diagonally. Don't trap liter on the bottom. Alright, and then I'm going to solve for liters, but before I can do this, I got to get this to moles, so I'm going to convert the grams to moles first and drop it in there. I have 2 sig figs here, I have 2 sig figs here, so I'm going to have 2 sig figs when I'm done. Okay. So don't worry about it till the end. Alright, so let's do the math here. I got 5.0 grams of oxygen. That's O2. O2, keep in mind. And that's 16 times plus 16 is 32 grams per mole. So 5, rid of grams, go to moles. 1 mole is 32 grams. And now we're getting this. 5 divided by 32 equals 0.156 moles. Alright, so then we're going to use this formula right here now. So moles, 0.0156 divided by molarity, which is what I want, 0.0010 molarity, and what do we get for an answer? So it's going to be 0.001 divided by the previous answer on my calculator, 0.0064. 0.0064. That's my calculator gave me. That's 2 sig figs, and I'm going to leave it. This would be liters. Indicate your answer by putting a square around it. Alright, next one here. Okay, so now those are the main 3 ways we do things. And I can't really make them any more complicated. The first one, just leaving it. I could have solved a gram off of this guy, but we didn't. But did 2 other examples with grams. So this one has a gram here, and solving for moles and grams. So here's using grams, but solving for liters. So now we're just kind of reviewing here a little more. It's all going to just start cycling through, although we have some slightly new concepts here. Alright, so molarity is, again, is moles per liter. 58 grams of sodium chloride dissolves in 0.1 liters of water. Write out the dissolving equation. Okay, so it's NaCl goes to Na plus Cl minus. Okay. What's the concentration of NaCl? Okay, so we're looking at molarity. Put it over here. Molarity equals moles per liter. Alright, so in this case, let's convert our grams to moles. Of course, we just mentioned that NaCl has a molar mass of 58. So we have 1 mole. 58 grams, grams to moles, 1 mole, 58 grams, so we have 1 mole. So if I have 1 mole of this, I will get 1 mole of this and 1 mole of this. So if we draw a picture of this guy, it's just going to look like this, Na plus Cl minus. If I dropped in 6, it's just 3 of these NaCl's, I would get 3 of each of them. Okay, and they'd be in equal concentration. So what's the concentration of NaCl? Well, okay, so it's 1 mole divided by 0.1 liters is 10. 10 moles per liter. That is the answer for that guy right there. Second one. What's the concentration of each chloride ion? Well, if I have 1 mole of this, I got 1 mole of that. So the chloride ion concentration is just 1 mole of chloride ions divided by 0.1 liters, and that's also 10. And that's the answer to that guy. So we're kind of introducing some interesting ideas here. Is that if I have a 10 molarity solution of NaCl, that guy is also, because it's breaking apart into its separate now, only ionic compounds do that. This guy would be 10 molar, and this guy would be 10 molar of each concentration. Notice our particles double. So if you're blindly looking at particles, our ions concentration, that would be 20 mole per liter. That's a pretty high molarity, but either way. Next. Alright, 47.1 grams of magnesium chloride. Now, I don't know what that, let's check it out. Magnesium chloride. Now, magnesium is about 24.3, and the chlorides are 35.4, and there's 2 of them. Let's see what we got for a molar mass here. 35.4 plus 35.4 plus 24.3 equals 95.1. So this whole thing weighs 95.1. Alright, so in this situation, what do we got? Okay, so I'm going to convert, I want the dissolving equation. Okay, so magnesium chloride goes to magnesium 2 plus, now mind I get 2 chlorides. So this would be magnesium, and I get a chloride and a chloride. If I dissolve 2 of the magnesium chlorides, I would get 2 magnesiums, which we show our charges, but I get 4 of my chlorides, notice, because they come in a 2-to-1 package here. So let's figure out our moles here. Looks like I'm pretty close to half. Let's see it. 47.1 grams. Get rid of grams and go to moles. 1 mole is 95.1. So 47.1 divided by the 95.1 is almost exactly 0.5, and if you go with 2 sig figs or even 3 sig figs, it's just going to round 0.500 moles. So I got 0.5. Alright, so I got 0.5 moles of this guy. 0.5 moles of this. And when I dissolve, remember for every one of these I get 1 and 2. So I'm going to get 0.5 moles of this and 1 mole of that. Just visually, hopefully you can see that. Okay, so what is the concentration of the magnesium chloride? Well, this is my moles, so it's going to be so the magnesium chloride is 0.5 divided by 0.1 equals 5. So the answer to this guy is 5 moles per liter. That's the moles of the magnesium chloride divided by the volume. What's the concentration of the chloride ion? Well, I got 1 molar here. 1 mole divided by 0.5 liters is, in this case, double that to 10 moles per liter. So that guy doubled. So in this situation, let's just grab our down here, give it a little more room. So in this situation, important key thing to note here. If I have 5 moles per liter of magnesium chloride, here's a shortcut. And this is breaking apart into magnesium ions and chloride ions. The magnesium ion is just going to be 5 molar, and there's one of them present. 1 times 5 is 5 moles per liter. That's that guy. 2 times 5 is, for that one, is 10 moles per liter. So we're doubling our concentrations of our ions, because this guy doubles. Just take the number of things you have and multiply it times the original concentration, and that tells you how much you got. Okay? Unique little twist to that question. Alright, can you determine the concentration of ions in a solution by simple inspection? Okay, that's kind of what we just talked about here. So I have 0.5 moles per liter. Therefore, we're at the dissolving equation. AlCl3 goes to Al plus 3 Cl minuses. Determine the moles of each. Okay, well, we can't do that because I didn't give a volume here, so I'll have to do that here. Let's go with, I don't know, 0.5, let's go with 1 liter. Okay, 1 liter, easy enough, because 1 liter, that means we have 0.5 moles of this. We have 0.5 moles of this, and we have 1.5 moles of that guy from the concentration of each. Okay, so it's 0.5 divided by 1 liter, 0.5 divided by 1 liter, and 1.5 divided by 1 liter. And of course this gives you 0.5, 0.5, and 1.5. Now as I mentioned earlier, a shortcut would be to take this concentration, just multiply it by the number of things that you're breaking into. This would be 0.5 times 1 is 0.5. 0.5 times 3 is 1.5. So here, let's just do this really quickly. You can pause the video and try your own. This guy here is 0.5 concentration. This guy is 0.5 concentration. This guy is 0.1. This guy is 0.2. This guy is 0.25. This guy is 0.5. Pretty simple. But there's an underlying idea behind it that it's breaking apart into those number of pieces. Okay. So we're going to add some water to it, but we're getting to 20 minutes, which is the limit to what I really want to keep this at. So we'll pick up dilutions, thing called dilution, in the next video.